This is chapter 3. This is chapter 3 going into what we call logic gates. So basically what we're going to be talking about in this chapter is the various different types of logic gates. So let's get into some definitions here, and let's talk about some digital circuitry. Let's get into let's get into the meat of this class here. So logic gates. Basic building blocks of any digital circuit. That's what a logic gate is, a basic building block of any digital circuit. It is the fundamental. It is needed in order for us to have computers running. So we have logic gates. We must have what we call a logic function, a logical function. A logical function is a logical task that needs to be performed. It's a task that needs to be performed. Okay, so there's different types of logical functions we use. There's what we call AND gates, Nand gates, OR gates, exclusive OR, and etc. There's a bunch of them, and we'll get into them. So all these logic gates actually are built on the idea of TTL, and TTL stands for transistor logic. So in our Groves book, we're actually going to be looking at, okay, how do we take a transistor and make an AND gate or an OR gate? Once you have that idea behind you, the fundamental idea behind you, now what we can do is scale it down really small and put this into what we call an integrated circuit. So an IC is called an integrated circuit. Integrated circuit. And in an integrated circuit is transistors. Basically, there's a lot of transistors in there. When we say there's a lot of transistors in there, we're talking in small cases maybe 1 million, in large cases billions of them. And also there's small amounts of resistors and diodes. And so these integrated circuits are what make our life today makes it a lot easier, makes it a lot less complex. So for example, we got a computer to do a lot of our tasks today. All right, we were talking about transistor logic, TTL logic. The other type of logic we actually have is called CMOS. That's complementary metal oxide semiconductor. These are really static sensitive. We have both in the lab. We're going to be basically using TTL. Basically, our TTL chips use a 7400, and I'm going to use the X as the N. And then the metal CMOS, or the complementary metal oxide, uses the 40OXXX series. So we'll get into that very shortly here in the lab, actually setting up these circuits. So the first type of circuit we want to look at, a logic circuit, is called the AND gate. This is sometimes called the all or nothing. This is the all or nothing gate. When we say it's all or nothing gate, meaning that if you have an input 1 in order to get an output of 1, you have to have both inputs. Everything has to be a 1. It has to be a high. It has to be a high. So an AND gate, if we take a look at it, they give a little bit of a description in the book using an A and B input. So what I'm going to do is draw out what the gate looks like. So if we actually look at it, this is an AND gate. So you have an A input and a B input, and then we're going to have a what's called Y output. In the book, they actually show, okay, a light turning on. Let's draw a circuit on that. Let's do a circuit on that real quick. So if I actually have a battery here, and then I have two switches, switch 1 and switch 2. There it is. There's the word and. Switch 2. And then we have, let's say, an LED. An LED. And we're going to tie that to ground. And this is going to be 5 volts. And this is plus minus. So an AND gate is basically this switch and this switch must be on in order for this light to turn on. So in this case, we need to have a 1 on the A and 1 on the B. So let's call this A and let's call this B. So if we have A on, that means this switch is closed. And B on, this switch is closed. This light will turn on. So let's draw a truth table. Truth table basically gives us an idea of what's going on in the logic gate itself, the truth table. So this is the logic symbol. This is the logic symbol. Now we need a truth table. A truth table is basically a mathematical representation of what's going on inside this gate. So if we draw a truth table on this, A, B, and then you have your Y output. That's really good. Can't draw straight lines. So I'm going to try to draw this a little better. There we go. So basically, if we start putting in binary numbers in here, zeros and ones, where a zero, remember a zero is equal to no voltage, and a 1 is equal to 5 volts. So if we start out with 0, 0, and we put it in here, well, if we do this, and we do it mathematically, A and B is equal to Y. Here's the mathematical symbol. That is what's going on in here. So A and B. With 0 and 0, well, it has to be a 0. So a 0 and a 1. So we put now a 0 and a 1 here. Well, we do it. 0 times 1. Well, 1 times a 0 is going to be a 0. If we do a 1, 0, still going to be a 0. But if we do a 1 and a 1, it becomes a high. Because remember, 1 and 1 is equal to 1. So an AND gate, it doesn't matter how many inputs you have. You could have 1,000 inputs. In order for that output to be on, we need to have A and B to be high. So what would be a good example of a circuit we could draw with an AND gate? So if I actually take this and I take it over, and let's say we want to have an LED go on, a visual indicator go on. So I draw it out. So I got A and B. Now I could do is I could take this to a switch or some sort of switch on A and B, and in order for this guy to turn on, I need to have a high. There's a circuit diagram for it. Now let's look at an OR gate. That's the second type of logic gate we have. This is called the any or all gate. So basically on this one is that if we have a 1, we'll always get a 1 out. It doesn't matter. So we can have 1 in and we get 1 out. So to get a better understanding what an OR gate is, think about a bunch of switches that are in parallel. Remember, an AND gate, the switches are in series. So if we actually redraw the circuit, the same circuit we had above, but this time I do is put the switches in parallel. So I have a switch here. Let's call this A, and there's my parallel circuit. Let's call this B. And then I'm going to do is tie this back up, but I'm going to tie this to my LED. And you know my LEDs have to be connected to resistors, but for the simplicity of it, keeping the resistor out, my grounds are connected together. So basically this is an OR gate. It's A or B. See how they're in parallel with each other? So if we select A, you get 1 out. If you select B, you get 1 out. It doesn't matter. So in this case, we can represent this A and B again in Y output. And our truth table is basically a listing of everything that's going to happen in that OR gate there. So I have, again, A, B, Y. So if I put in my combination, and then I look at it, well, I can actually get this. This is the mathematical equation for OR gate. That's not a plus, that's an OR. This is not a multiplication, that is an AND. Don't get these confused with your mathematical symbols. So this is A or B is equal to Y. So if we put it in the truth table, 0, 0, well, we're going to get 0. 0 and 1, we're on 1 and 1. You notice that we're going to get all 1s. It doesn't matter. We're going to get all 1s out. So if we want to look at a circuit on this, what we can do is similar to the above. And this is the symbol of it. You notice there's different symbols for everything here. A, B. Again, I'm going to have a resistor. And when I talk about a resistor, and I could put it up here too, R is equal to, let's say, 120 ohms. R is equal to 120 ohms. Let's call this R1. And then I got my LED, and goes to ground. And the little arrows like that indicate light. So that's an AND gate and an OR gate. Plain simple. All right, the next one we're going to want to look at is called the inverter, and also we're going to talk about the buffer, and that'll be end of part A on here. But the inverter, basically what it's going to do is going to take and invert it. So if we look at the symbol for it, if you look at it, you notice I have a circle over here. Anytime you have a circle over here, that means you're going to be inverting it. So this is if you see a circle, this means inverting. So if we look at this, we can say that Y is going to be equal to a not. So basically, if we have a 1 in, what are we going to get? A 0 out. So if we look at the truth table, if we want to look at the truth table, this is the mathematical symbol for it. If we look at the truth table on here, and I do that. So if I have a 0, I have a 1. If I have a 1, I have a 0. It's inverting it. Okay, so this is called a not symbol. This is called an inverter. We're getting something, we're doing the opposite. Likewise, looking at similarity, and this is what confuses a lot of students, is we have a buffer. Notice the difference between the two. This is a buffer. The buffer is used to help drive higher current devices. We also use it in computers quite a bit to help drive some signals on the bus line, etc. So keep it that way. A and Y. So if we look at the truth table on this, so actually let's do the mathematical equation. So we can say that Y is equal to A, and then I can say that in the truth table here is A and Y. So 0 and 1 again, I get a 0 and a 1. That's all there is to it. Sometimes the inverter is called a not circuit. It's called a not circuit. That's because whatever's coming in A is not going to be what's over here. It's actually going to be the opposite of it. All right. If you have any questions. Most of the time, the buffer circuit, the buffer will actually have control on, and that's the last thing I'm going to talk about. Oh, I forgot about that. That's why I'm back on here. So if we look at this A and Y, we have a control line that comes over here. And you notice the control is right there. And if you look at the computers and stuff, this is similar to what you'll find. So we can actually turn this integrated circuit on, this NOT gate on, by putting a control line to it. A good way to look at that is, let's say control is C, and then we have A, and then we have Y as the output. So again, if I have a 0 and a 1, here's what's going to happen. If I have this control, let's say this control has to go high because there's no. If there was a circle here, that means it'd be a low to turn it on, but this requires a high. So let's say this is a low. Well, if this is a low, this is not going to be, so there's nothing going to happen over here. Nothing's going to happen. It's going to be at its original state. It's going to just sit there and it's going to do anything. So whatever state it's at, it's going to be. That's why I have an X. But if I have this at a high, and now I go with a 0 and a 1, and I start putting in, and this goes high, well, this is going to turn this guy on. So that's going to go to 0, and that's going to go to a 1. Now you're probably asking, how can I tell if it's a 0? Well, there's a way to actually do that. And we can actually do that is using a logic probe. We can actually put it to a logic probe. That specialized tool that I said, we can put it into a logic probe. So if there's any other questions you have about this chapter and part A of it, please email me and I'll be more than willing to discuss it with you. Thank you.